Welcome to The Explainer. Today, we're diving into a piece of tech that literally challenges the very foundation of Web3 and distributed ledgers. We're talking about Hedera and its underlying hashgraph consensus algorithm. You know, if you've spent any time at all in the crypto space, you are completely used to blocks, chains, and miners, right? Well, today, we are taking those concepts and throwing them right out the window. So let's start with a really fundamental question. Does a secure, decentralized ledger actually require miners to pack transactions into slow, sequential blocks? Think about it. For the longest time, the entire industry just assumed the answer was a resounding yes. That sequential bottleneck was just kind of seen as the accepted price we had to pay for decentralization. But as it turns out, the answer is absolutely no. Thanks to a 2016 invention by Leemon Baird, we have something called the hash graph. It's a directed acyclic graph, or a DAG for short, that's connected by cryptographic hashes. It achieves asynchronous Byzantine Fault Tolerant consensus. That's a mouthful, but it's basically the gold standard for security, and it does it without ever needing a single traditional block or a miner. No way, right? Okay, here's our roadmap for today's explainer. First, moving beyond the blockchain. Second, a concept called gossip about gossip. Third, reaching virtual consensus. Fourth, zooming out to the Hedera network. And finally, bridging to Ethereum. All right, part one, beyond the blockchain. Let's get right into the absolute basics of how these computers actually manage to talk to each other without some miner bossing them around. Which brings us to part two, gossip about gossip. To really wrap our heads around this, we have to look at the core engine of Hashgraph, which is delightfully called the gossip protocol. It all starts out remarkably simple. Every participant keeps a copy of the hash graph right in their memory. Imagine we just have 4 network members. Let's call them Alice, Bob, Carol, and Dave. They each start by creating a single event in their memory. You can think of an event as just a tiny little data container. Now, watch this gossip mechanism in action. Imagine Bob just randomly calls up Dave over the internet and sends him all the events he knows about that Dave doesn't have yet. Dave records the fact that this sync happened by creating a brand new event, connecting his timeline to Bob's. It's literally just 2 computers syncing up. And every single time these nodes gossip like this, they create a new event. But what's actually inside that container? Well, it holds any transactions a user wants to send, a timestamp, a digital signature, and this is absolutely crucial, the cryptographic hashes of the 2 previous events right below it. We call those its self-parent and its other parent. This is what mathematically locks the history in place. So, fast forward a bit. As these nodes constantly call each other at random, sharing everything they know, the idea spreads like wildfire. They create this incredibly fast, interconnected web of events. This is the hash graph itself, growing upward over time, forming a completely unchangeable record of exactly how and when everyone communicated. Okay, on to part 3, reaching virtual consensus. Because, just gossiping and sharing data isn't quite enough to run a global financial ledger. We need to figure out how these computers agree on the exact mathematical order of all these events, completely without a central referee. Enter a totally fascinating 4-step virtual voting process. Traditional networks send massive amounts of voting messages back and forth to reach consensus. Actually, scratch that. It's more like they flood the network and bog it down. But in Hashgraph, nodes figure out the timeline purely by looking at the math of the graph itself. They run virtual elections in their own memory without sending a single extra vote over the internet. So how does that math work? Well, every participant independently calculates when a new round of communication is created. And the very first event that a member creates in that new round is mathematically designated as a witness. It's like a checkpoint. The nodes then use the graph's connections to hold an election for each witness, deciding if it's considered famous. To be famous, a witness has to be seen by many of the witnesses in the very next round. They trace the math downwards, and if they can trace paths going through more than 2/3 of the network, which is a supermajority, then boom, the election is decided. The network reaches total consensus on the timestamp and the order of transactions instantly. All right, part 4, the Hedera network. We've mastered the micro-level algorithm, so let's zoom out to the macro-level reality. How is this actually used in the real world? It started with Leemon Baird's 2016 technical report. By 2019, this brilliant piece of math evolved into a live public mainnet. Then, in 2022, they open-sourced the algorithm under an Apache license. And just recently, in 2024, the whole source code was handed over to the vendor-neutral Linux Foundation under the project name Hero. Talk about an evolution. Now, unlike purely decentralized chains where anyone can just spin up an anonymous Lightning node, Hedera took a totally different route for enterprise adoption. It's governed by a council of massive global organizations. We're talking heavy hitters: Google Cloud, IBM, Deutsche Telekom, FIS Global. They are the ones actually running the mainnet nodes and voting on network upgrades. And to fuel this enterprise-grade machine, they use a native cryptocurrency called HBAR. Because that gossip protocol is so incredibly lightweight compared to mining blocks, the network enjoys extremely low and predictable fees. It completely avoids those crazy volatile gas fee spikes that plague other networks when they get congested, all while keeping that ironclad ABFT security. Finally, part 5, bridging to Ethereum. We've got this super unique, blockless, corporate-governed network. So how on earth does it fit into the broader Web3 ecosystem where developers are so used to building on Ethereum? Well, if you're an EVM developer, there are a few core differences you really need to know. You're trading standard BFT for a ZBFT consensus. You're obviously using HBAR instead of ETH. The state is tracked via a virtual Merkle tree rather than a Merkle-Patricia tree. But the biggest takeaway for users? You're interacting with low, predictable fees instead of wild variable gas costs. Under the hood, there's also a major structural difference in how keys are managed. Hedera natively supports advanced ED25519 cryptography, dynamic key rotation, and really complex threshold keys. Ethereum relies basically just on standard ECDSA keys. Hedera does provide aliases, so your Ethereum tools still work, but those native Hedera accounts are just way more flexible. Now, here is a massive gotcha if you're migrating a smart contract. You absolutely must account for the math. Hedera native tokens defaults to 8 decimals of precision, while standard EVM tokens expect 18. If you don't adjust your contract's logic for this, your financial calculations are going to be completely out of whack when bridging assets. But despite those architectural differences, Hedera has built some incredible bridges. Thanks to their JSON RPC relay, developers can deploy standard Solidity smart contracts using the exact same tools they already know and love: Hardhat, Foundry, MetaMask, the whole shebang. They even support jumbo Ethereum transactions for deploying massive, complex contracts directly onto the hash graph. So we've seen how a simple gossip protocol between just 4 computers can scale into an enterprise-governed EVM-compatible powerhouse, all without ever mining a single block. Which leaves us with a pretty fascinating thought to ponder. As the demand for speed, scale, and low fees pushes traditional blockchains to their absolute limits, is the future of Web3 actually just a graph built on gossip? Thank you so much for joining me on this explainer. I hope this really helped you visualize what makes Hedera tick.